Most solutions, if you add an acid or a base, the pH will change significantly. So, if you have pure water and you add some acid, the pH is going to go down very quickly. Buffers resist that pH change. So buffers will contain a weak acid and its conjugate base, or a weak base and its conjugate acid. And you need to have significant amounts of both of them. If you just have a weak acid or a weak base, there's not enough of the conjugate ion present to act as a buffer. The word buffer, out of the corner of my eye, I keep seeing buffet. It's very distracting. So how do you make a buffer? Well, here's one way you can make a buffer. You can take a weak acid. Here in this example, we're using acetic acid. So you put the weak acid into the solution, and then you're going to add the conjugate base. So the conjugate base would be acetate ion. You can't just have acetate ion, so you need to have something like sodium acetate or potassium acetate, and you add that into the solution. So now in the solution, we have a significant amount of the acetic acid molecules, but also a significant amount of the acetate ions. If we just have the weak acid, it's mostly going to be acetic acid molecules, and there will only be a few of the acetate ions. So we need a good quantity of both to have a buffer. Any questions yet? So which solution is a buffer? First choice, all of these are 0.1 molar. So this is HNO2 and HCl. Is that a buffer? No. This is a weak acid, but this is not the conjugate base, right? So that doesn't work. How about HNO3? Come on, pointer. And NaONO3. No, why not? It's a strong acid. It has to be a weak acid. How about this one? HNO2 and NaCl. Yeah, this is neutral, and this is a weak acid, but we need the conjugate base. So hopefully this will work at the end here. So here's HNO2 and sodium nitrite. So when you see an ionic compound, you need to be able to identify what the ions are. So that's sodium ion and nitrite ion. Right, here's our weak acid. When that ionizes, it forms hydrogen ion and nitrite ion. So by adding sodium nitrite, then we can get a significant amount of this nitrate ion as well as a significant amount of the nitrous acid. You can't, so what is this sodium going to do? It's going to float. This mingling is just hanging around. It's just there to watch. It's a spectator ion. So let's look at a solution that has 0.1 molar acetic acid and 0.1 molar sodium acetate. So here's the acid ionization equilibrium for acetic acid. And, there's a Ka for that, an equilibrium constant. But if we have acetate ion also, what does that do to this equilibrium? If I add something to the product side, how does that shift the equilibrium? It shifts it to the left. So the acetate ions being present are going to cause the acetic acid to ionize even less than it normally would. So this is a less acidic solution than you would expect. This is called the common ion effect, because this is a common ion to that acid. So let's calculate the pH of a buffer solution that is 0.20 molar in acetic acid and 0.10 molar in sodium acetate, and we're given the acid ionization constant. Well, I'm going to use A just because it's fewer letters to write. So this is acetate and this is the acetic acid. So we're calculating a pH. What kind of a table do we need? An ice table. So we'll look at the initial concentrations, the changes, and what we have at equilibrium. So when we say a solution is 0.2 molar acetic acid, this is a weak acid, what we mean is that they're 0.2 moles per liter of the acid. You put it in the water and then it's going to ionize. That's not reflected in this 0.2 molar. So it starts out at 0.2, and then the sodium acetate, this is going to dissociate completely, right? The sodium's a spectator, and then we've got acetate here, and 0.1 molar acetate, so that's what we've got over here. And what's the initial concentration of hydrogen ion? Essentially 0. Is this reaction going to proceed in the forward direction or the reverse? Forward. It really can only go forward because this is already at 0. We can't have less than that. So we're going to lose X amount of HA, and we're going to gain X amount of these two products. So we've got 0.2 minus X, and we have X, and we have 0.1 plus X. So we've got our acid. Got our equilibrium expression here. So we're going to put these values here in. Those are the equilibrium concentrations. So we've got X times 0.10 plus X divided by 0.200 minus X, and that equals the acid ionization constant that was given. I knew I forgot something. Okay, so what could we try first here to make this a little easier? We'll try X is small, right? So if X is small, that means this is small enough we can call it 0, and that's small enough we can call it 0. And then we'll end up with X being equal to 0.2 times 1.8 times 10 to the minus 5 divided by 0.1. So to check the validity of that, I'm going to divide it by the smallest one. Divide by 0.1, times 100 and 0.036%. The x is small, approximation is valid. So this is x. We're trying to find the pH. X is equal to the equilibrium concentration of hydrogen ion.
I'm sorry, which one you divided again?
You want to divide it by the smaller one, right? So this is, I think, one of the first times where we haven't been adding and subtracting it from the same number. So to find out if this is actually small relative to 0.1 and 0.2, we want to look at it relative to the smaller one.
Okay.
Because it'll be a larger percentage of 0.1 than it is of 0.2. Does that make sense? So the 5% idea for x is small, we calculate x, and then we compare it to the things it would have been added to or subtracted from.
Okay.
If it's less than 5% of these things, then it's considered a valid approximation. It doesn't, we're not going to do anything with this.
Okay.
Yeah. So that tells us that our hydrogen ion concentration is 3.6 times 10 to the minus 5. And so pH and that should have two significant figures, so 2 decimal places, a pH of 4.44. Any questions? Yeah.
Do you always have to do x is small, or can you just plug it in the calculator?
You do not always have to do x is small. You can, if you've got a calculator that does, with a number solver like this one, you can always use that. Yeah, you can always use that. .44. So here's an equation with a really long name. The Henderson-Hasselbalch equation. This always reminds me of David Hasselbalch, but it's not. The Henderson-Hasselbalch equation. So we can derive an equation that relates the pH of a buffer solution to the initial concentrations of the buffer components. Hopefully I can remember where I'm supposed to go with this. So we can write the equilibrium constant expression for this. I'll use hydronium since they put it in there. So if we're trying to find the pH of the solution, we want to rearrange this equation to solve for H3O+. So I'll end up with H3O+ is equal to Ka times Ha over A minus. So I brought this to the top and I took that to the bottom. So these would be the initial concentrations. If the x is small approximation is valid, though, then we can say that the equilibrium concentrations of these are essentially the same as the initial concentrations, right? So x is small, must be valid. Well, that's the hydronium ion concentration. How do we get the hydrogen ion concentration? The negative log of that, right? So the negative log of the hydronium ion concentration is going to equal the negative log of this other mess. If you take the log of two things that are multiplied, it's the same as the log of each of them added together. So I guess math people would say the log of x times y is equal to the log of x plus the log of y. So then this is equal to the negative log of Ka minus the log of HA over A minus. Well, it's the negative log. So it's the negative log of this one plus the negative log of that one. Well, so negative log of hydronium ion concentration is pH. What's the negative log of Ka? pKa. So pH is equal to pKa. Well, negative isn't very nice there. I can take this negative sign and make it positive by inverting this fraction. So plus the log of A minus over HA. And so we usually write it like this: pH is equal to the log of A minus over HA plus pKa. And that is the Henderson-Hasselbalch equation. You do not need to know how to derive it. But any questions?
I just need a little more time to copy.
So there it is, the Henderson-Hasselbalch equation. It's the base over the acid. You can do this as long as the X's small approximation is valid. When might that work? Well, if your initial concentrations are not too small and your K is fairly small. I honestly don't know what that means. Acid and base greater than... I think it means that the acid and base concentrations initially need to be like more than 100 to 1,000 times larger than the Ka. You can always use the equilibrium approach. Make an ice table and solve it. That always works. This works when X is small. Okay, let's do an example. Calculate the pH of a buffer solution that is 0.250 molar in HCN and 0.170 molar in KCN. And then we're given Ka and pKa. Use both the equilibrium approach and the Henderson-Hasselbalch approach. So I'll do the equilibrium approach first. This acid doesn't have too many letters in it, so I'm going to go ahead and use its actual formula. Making a nice table. Initial concentrations, so the acid is 0.25. So 0.250, and then it's 0.170 molar in KCN. So that potassium is just a counter ion. It's a spectator ion. It's there because cyanide can't come to this event by itself. You have to have someone with you. I don't know. Couples only, yeah. My analogy maker isn't working very well right now. So we'll just ignore that K. This is the cyanide concentration. So that is the conjugate base here. So 0.170 molar in that. And as always, the hydrogen ion concentration is approximately 0. Then we're going to look at the change. This will go down by X. This will go up by X. This will go up by X. So we get 0.250 minus X and X and 0.170 plus X. So here's our Ka, 4.9. Times 10 to the minus 10. And that's going to be equal to the hydrogen ion concentration times the cyanide concentration, which is those two guys down there. It's helpful if you copy the right numbers down. Just divided by this guy over here. These concentrations are relatively large as far as molarities go. A 1 molar solution is actually quite concentrated for most things. So, these are like 0.25 molar. That's quite a bit. If it was 0.0000025 molar, that's not very concentrated, right? So here we have relatively large concentrations, and we have a very small Ka, and so the X is small approximation is probably going to be good here. That's too fat. So we're going to end up with X being equal to 4.9 times 10 to the minus 10 times 0.250 divided by 0.170. Come on, calculator. So 7.2059 times 10 to the minus 10. Is this less than 5% of 0.17? Yeah, it's way less. So then, to find the pH, I'm going to take the negative log of that concentration, and we'll find out that the pH is 9.14. I'm going to put 3 sig figs. 9.142. These have 3 sig figs. The Kas only have 2. If we decide we want fewer, we can always knock one off. Okay, so any questions about that one? That's just doing a nice table, like we did in chapter 17. So then it says also to use the Henderson-Hasselbalch approach. So the pH is equal to the pKa plus the log of the base over the acid. I used to have trouble remembering which one goes on top, and it matters. So this is what makes sense to me. When we do these equilibrium expressions, it's always the products over the reactants, right? The products over the reactants. Well, the conjugate base is the product, and the acid is the reactant. And so this is like part of an equilibrium constant expression. So it's the base over the acid. So we're just going to plug in the numbers. We've got 9.31 is our pKa, plus the log of, the CN is 0.170, the HCN is 0.250, 9.31 plus log of 0.17 divided by 0.25. 9.1425. Here with this pKa, we definitely should have just the two places here. So that gives us 9.14. And we also got 9.14 over here. Any questions? Which one was faster? The funny named equation.
Yeah.
That needs a nickname. So Jonathan, it's your job to come up with a good nickname for the Henderson-Hasselbalch equation. I want it before you leave tonight, okay? Yeah, so this is a lot faster, right? So then sometimes people are tempted to use this inappropriately because it's easy, right? It's only good for buffer solutions. Only good for buffer solutions. 9.14. So calculating pH changes in a buffer solution. So buffers resist change in pH, but they don't eliminate it. So there will be a change in the pH, but it's just a lot smaller than if there was no buffer. So to figure out what the change in the pH is, we need to look at two different parts of the problem. We're going to look at a stoichiometry calculation. So we're going to look at how that addition changes the relative amounts of acid and base. And then we're going to look at the equilibrium calculation. So we'll calculate the pH based on the new values of the acid and base concentration. So there's two parts. Buffer contains the weak acid HA and its conjugate base A-. The weak acid has a pKa of 8.42. The buffer has a pH of 4.25. Which statement is true of the relative concentrations of the weak acid and conjugate base in the buffer? Is there more acid than base, more base than acid, or are they equal? How do we even think about this? So we're going to add the log of the base to acid ratio to the pKa. So what happened here is the pH is smaller, right? So that tells that this value must be negative. And, maybe you can think this out, maybe you can't. So it's like, well, if the base is larger than the acid, then this number is going to be greater than 1, right? So let's maybe call it 2, right? What's the log of 2? It's positive, it's 0.3. So that would make the pH greater. So it must be the opposite. The acid must be higher in concentration. Another way to think of it is actually much simpler. So the pH of this is less than the pKa. Is that more acidic or more basic? It's more acidic. So then we would expect that there's a higher concentration of the acid than the base. Okay. So we're going to do an example. We've got a liter of buffer. It's 0.1 molar in the weak acid and in the conjugate base, and we're going to calculate the pH after adding 0.025 moles of a strong acid. So what we want to do is we want to look at the stoichiometry and figure out how much the amounts of acid and base are changing. We're working with moles here, not molarity. This is not a nice table, okay? And if you look at the letters here, BAA, we called it a BA table. Turns out I actually really don't like these BA tables, but we'll start with them. So before the addition, and so we're adding a strong acid, right? So adding a strong acid means we're adding hydrogen ions. So what is the hydrogen ion going to react with? It's going to react with the conjugate base to form more of the weak acid. So initially, we're going to start with essentially 0 hydrogen ion, and we've got our initial amount of moles of acid and base. So there's 1 liter of this, so it contains 0.1 moles of each, the acid and the base. And then we're going to look at how it changes. So we're adding this much strong acid. So we're adding this acid here. So then what happens? Well, a reaction is going to happen, right? This is going to react with that and form some product, and we need to figure out how much. What we're going to do is we're going to assume that it goes to completion. We'll worry about the equilibrium next. We're not worrying about an equilibrium here. So I've got 0.025 and I've got 0.1 moles. Which is the limiting reactant? This one, right? So that tells me all of this is going to get used up. So it's going to take out 0.025 moles of that, leaving me 0.075 moles. And together, those are going to give me an additional 0.025 moles of this. Does that make much sense? You can say no. I don't like this table. So I'm going to get rid of it. In my slides, I can do what I want. Okay. So let's just look at what is in this solution in moles? I got 1 liter of this, and so I can calculate the moles of each of those. I've got 0.100 moles of that, and I've got 0.100 moles of that. And then I'm going to add what? I'm going to add 0.025 moles of strong acid. And so this is, we're doing a complete reaction here. How is this going to react, and what are we going to end up with? So I'm going to use up all of the smaller one, right? So this one's going to get all used up, so I'll end up with 0. And that is going to use up 0.025 moles of that, leaving me with 0.075 moles. And that's going to create 0.025 moles of this, leaving me with 0.125 moles. I think that makes more sense. One of the dangers, though, is that you are talking about a starting point, an initial, and a change. But this is the end, which also starts with an E, but it's not an equilibrium. It's still not an ice table, okay? It's not an ice table. We'll do that next. So now we're going to look at a solution that has 0.075 moles in 1 liter of the conjugate base and 0.125 moles in 1 liter of the conjugate of the weak acid. So when we add a small amount of strong acid, that's equivalent to changing the initial concentrations of the buffer components. So here's our new concentration. This is molarity now. It was 1 liter, so the moles and the molarity are the same. 0.125 moles per liter of the acid, approximately 0 of the base, and 0.075 of the acid, of the conjugate base, right? And so then we get these, and we end up with these equilibrium expression, right? So we can either work the full problem like that, or we can use the Henderson-Hasselbalch equation. Any questions? If we are adding a strong base to the buffer, it's the opposite of adding an acid. So the strong base would be that amount of hydroxide ion. That's going to react with the weak acid. So we're going to look at whatever is being added as completely reacting with whatever would neutralize it. And then we've got a new problem with new starting concentrations to find the pH. So if we add a small amount of strong acid to a buffer, it's going to convert a stoichiometric amount of the base to the conjugate acid, and we're going to see a decrease in the pH. Which makes sense, right? You add acid to something, the pH should go down. If we add a little bit of strong base to the buffer, the pH is going to go up a little bit. But it's not going to go up nearly as much as if there wasn't a buffer present. Don't those look like dominoes? Those look like dominoes to me. Weird dominoes, but anyway. So, look at this and think about this as our initial buffer. We've got equal concentrations of the acid and its conjugate base. And that's represented by, we've got the same number of HAs and A minuses. If we add hydrogen ions to that, the hydrogen ions are going to react with some of these A minuses and form HAs, right? So now we're down one here, and we've increased one over there. If we add hydroxide to this, the hydroxide is going to react with the acid. And we're going to form an extra A minus, and we'll have one less of the HA. Does that make sense? I remember having to think about this for a while. Every time I tried to learn it again. It's really pretty cool when you think about it. Bless you. Okay, so let's look at this figure closely. Which image, A, B, or C, best represents the amount of hydroxide that was added to the buffer in part B, meaning this part. So here, how much hydroxide is getting added to give this result? A, it's going to be 1, right? Because adding 1 hydroxide converts one of these into those, right? It's going to take the hydrogen off to make water, and then the purple one will belong in this column. That make sense? A 1 liter buffer solution contains 0.1 molar acetic acid and 0.1 molar sodium acetate. Because the initial concentrations are equal, pH is equal to pKa, which is 4.74. Calculate the new pH after adding 0.015 moles of sodium hydroxide. So first, we're going to do a stoichiometry calculation. So we're adding a strong base. We're adding hydroxide. Is that going to react with HA or with the A minus? So if we add base, it's going to react with the acid. So that's going to react with the acid, and it's going to form water and A minus. You don't get that?
No, I said I only ever got B's.
Oh. So this is 1 liter of stuff. So how many moles of this weak acid do we have? 1 times 0.1 is... 1 times 0.1 is 0.1?
Isn't it divided by 1?
No.
Because it's moles already?
Oh, it's giving us some moles. I thought this was molarity. Okay, yeah. Thank you for the blank stares, because that was appropriate. Sorry. They tell us the moles. Usually they tell us the concentrations. So it's telling us we have 0.1 moles of that and 0.1 moles of this. And then we're going to add 0.015 moles of hydroxide. And this is really a limiting reactant kind of problem, where we're looking at whichever one is the smaller, that's all going to get used up. So all of the base will get used up, which is going to use up an equivalent amount of the acid and produce an equivalent amount of the conjugate base. I do that right? So we're going to look at the equilibrium again now. And so the HA is 0.085 moles in 1 liter would be 0.085 molar. The hydrogen ion is approximately 0, and the A minus is 0.115 molar, right? Let's use the equation. So the pH is equal to the pKa, which is 4.74, plus the log of the base concentration divided by the acid concentration. Did it go in the right direction? We added a base, the pH went up. So that doesn't prove anything, but it's encouraging. Any questions? Well, what about buffers that have a weak base and its conjugate acid? Those work as well. So the calculations are similar. So this is important. When using the Henderson-Hasselbalch equation, we need to first calculate the Ka for the conjugate acid of the weak base. It's really tempting to say, well, I'm just going to do it with pKb instead. But then there's other things that have to be done to the equation, and we don't want to go there. It's simpler to just calculate the Ka. I mean, how hard is that? The pKa plus the pKb equals 14, right? So calculating the pKa from the pKb is no big deal, and then you just use the equation as it is. So here's looking at a buffer formed by a weak base and its conjugate acid. So here's ammonia, put that in there, and then ammonium chloride. The chloride here is just the counter ion, a spectator. And so now we've got lots of ammonia and ammonium ions. So calculate the pH of 1 liter of a buffer solution that is 0.5 molar in ammonia and 0.2 molar in ammonium chloride when 0.01 mole of solid sodium hydroxide is added. And we're given the pKb. Stoichiometry first, then equilibrium. So what are we adding? We're adding hydroxide ion. Is that going to react with NH3 or with NH4+? Which of these? So this is the base, right? The base will react with the acid. The acid's the one with more hydrogens. So this is going to react with the NH4+. And that's going to make, that looks really weird, H2O plus NH3. That's better. So this time they did give us concentrations instead of moles. Here's my volume. 1 liter times 0.5 molar means I've got 0.5 moles of ammonia. And I've got 0.2 moles of ammonium. And we're adding 0.01 moles of hydroxide. Okay? So this is the one that there's less of. All of it is going to react. So we've got none of that left. So we're going to have 0.19. And over here, we're going to end up with 0.51. So for our 1 liter solution then, our starting concentrations would be for the ammonium be 0.19 molar, and for the ammonia is 0.51 molar. pH equals pKa plus the log of the base divided by the acid. What's pKa for this? It'll be 14, exactly 14, minus 4.75. 'Yeah, that's what I thought. 9.25. So this will be 9.25 plus the log of 0.51 divided by 0.19. Nine point 6788, so 9.68.